तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to the Prestressed concrete structures. This is the third lecture of Module 9 on special topics. In this lecture, we shall study two-way slabs, and first we shall introduce the different types of two-way slabs. Next, we shall learn about the analysis of two-way slabs. After that, we shall move on to the features in modeling and analysis. What are the different aspects in the two-way slabs which are different from that of one-way slabs, and then we shall move on to the distribution of moments to the strips in the two-way slab. When a rectangular slab is supported on all the sides and the length to breadth ratio is less than 2, it is considered to be a two-way slab. The slab spans in both the orthogonal directions. What we had seen last time for a one-way slab is that we designed the slab for only one direction, and in the transverse direction we provide nominal reinforcement. But for two-way slabs, it has to be designed for both the directions. A circular slab or other types of rectangular slabs with different types of support conditions which do not fall into the category of a one-way slab are considered as two-way slab. That means, say a rectangular slab which is supported on 3 sides or say 2 adjacent sides, these are also categorized under two-way slabs. Rectangular two-way slabs can be divided into the following types. First, flat plates. These slabs do not have beams between the columns, drop panels or column capitals. There may be spandrel beams at the edges. Let's first know these terms a bit more properly. If a column has a flared portion at its top, that is called a column capital, and if the slab is thickened around the column, it is called a drop panel. Now, in a flat plate, there are no beams, no drop panels or column capitals. There may be some beams at the edges at the exterior of the building, and those beams are called spandrel beams. These are called by a special name because it needs to be designed for torsion. The second type of two-way slabs is the flat slabs. These slabs do not have beams, but they have drop panels or column capitals. Thus, the difference between a flat plate and a flat slab is that a flat plate does not have even column capitals or drop panels, but a flat slab has those in the building. The third type is the two-way slabs with beams. There are beams between the columns. If the beams are wide and shallow, they are called band beams. That means a two-way slab with beams has beams running in between the columns, and if those beams are shallow and wide, then these are called as band beams. For long span construction, there are ribs in both the directions. and this type of slabs are called waffle slabs. The slabs can be cast in situ, which is also called cast in place, else the slabs can be precast at ground level and lifted to the final height. These type of slabs are called lift slabs. This is a modern construction method where, to reduce the amount of the formwork, the slabs are cast at the ground level and then they are jacked up to their final height, and this type of slabs are called lift slabs. A slab in a frame building can be a two-way slab depending upon its length to breadth ratio. Two-way slabs are also present as mat or raft foundation. That means, given a building plan, first as a designer we have to identify which slabs are one-way slabs and which slabs are two-way slabs. If the slabs are supported on all the four sides, then the decision is based on the length to breadth ratio. Two-way slabs are not only present as floors or roof, they are also present as mat, or which are also known as raft foundations. In this lecture, which are of course focus on only the floor and roof slabs. In this figure, you can see the different type of two-way slabs, rectangular two-way slabs. In the first figure, it is a flat plate where there are no column capitals or drop panels. The slab is supported only on the columns at the four corners. The second type is the flat slab where there are drop panels or column capitals, and the third type is a two-way slab with beams where the beams are highlighted by the dashed lines. The arrows are spanning in both the directions to represent that these are two-way slabs spanning in both the orthogonal directions, and hence they are to be designed for both the directions. L represents the length, which is the larger horizontal dimension, and B represents the breadth, which is the shorter horizontal dimension. The absence of beams in flat slabs and flat plates lead to the following advantages. First, formwork is simpler. Second, reduced obstruction to services. In present day buildings, there are heating, ventilation and air conditioning ducts, and for convenience, to avoid any obstruction for the ducts, flat slab or flat plate construction is adopted. The third advantage is more flexibility in interior layout and future refurbishment. That means, once the building has been made, then the client has his or her own choice to lay out the interior of the space. Now, this is more convenient if the building is made up of flat slabs or flat plates. Two-way slabs can be post-tensioned. The main advantage of pre-stressing a slab is the increased span to depth ratio. As per SCI 31802, which is the building code requirements for structural concrete published by the American Concrete Institute, the limits of span to depth ratios are as follows. For floors, it is 42, and for roofs, it is 48. The values can be increased to 48 and 52 respectively if the deflection, camber and vibration are not objectionable. Thus, we see that the main advantage of pre-stressing a two-way slab is to increase the span to depth ratio. The span to depth ratio of a pre-stressed slab is much higher compared to a conventional two-way slab. The following photographs show some typical types and the construction of prestressed two-way slabs. In this photograph, we can see a post-tensioned flat plate after construction. We can notice that there are no column capitals or drop panels, and see that the bottom of the slab is completely flat. That means this type of construction does not create any obstruction for the service conduits. In this figure, we can see a post-tensioned flat slab where there is a drop panel. You can see that the slab has been thickened around the columns, and in other columns also you can notice the drop panel. Here also, for most of the areas, the bottom surface of the slab is flat, and hence this type of construction also creates much less obstruction to the service conduits. This is the construction of a prestressed flat plate. We can notice that the silver ducts are the ducts for the prestressing tendons, and they have been given an appropriate profile for the placing of the tendons, which is based on the design of the flat slab. And also you notice that non-prestressed reinforcement is provided in both the directions for the temperature and shrinkage effects. Now, around the columns there is additional reinforcement to transfer the shear and also to transfer the moment from the slab to the columns. The two-way slab design needs special attention, and hence it stands out as compared to a one-way slab. This is a close-up view of the reinforcement around the slab to column junction, and you can see that the ducts have been spaced closely around the columns, and also the reinforcement is much higher around this slab to column junction, which helps to transfer the shear that generates in this junction. This photograph shows the end zone reinforcement at the anchorage end of the prestressing tendon. Bursting links are provided to resist the stress concentration that is generated after the prestressing operation. Also note that there is a spandrel beam which runs along the edge of the slab, and this spandrel beam is designed for torsion, and hence the links or the stirrups that are provided in the spandrel beam are closed. That means there is a complete circulatory path for the torsion in the spandrel beams. This is the detailing of the other end, which is the dead end, and see how the tendons have been enlarged to create the anchorage at the dead end. And here also you can notice the spandrel beam with closed stirrups, and also you can notice the end zone reinforcement to check the bursting due to the concentration of stresses. Once the concrete is cast and it attains a desired strength, then the slab is post-tensioned by hydraulic jacks. Now, in this photograph you can see that a hydraulic jack has been placed at the side of the slab, and the tendons are being stretched by this jack to the required amount of prestressing force. After the stretching of the tendons, you can notice that they are anchored in the anchorage block. You can see the wedges that is holding the tendon in place, and this anchorage block is transferring the pre-stress from the tendons to the concrete. Next, we are moving on to the analysis of two-way slabs. The analysis of two-way slabs is given in section 31 IS 456-2000 under flat slabs. The analysis is applicable to flat plates, flat slabs and two-way slabs with deflecting beams. If the beams are sufficiently stiff, then the method, which is based on moment coefficients given in Annex D of IS 456-2000, is applicable for two-way slab with beams. Thus, if it is a flat plate or a flat slab, then we follow section 31 of IS 456-2000. But if we have a two-way slab with beams, then we have to make a decision based on the stiffness of the beams. If the beams are not stiff enough and if the beams are also considered to be deflecting, then we should adopt section 31, which is similar to flat plates and flat slabs. But if the beams are sufficiently stiff that we can neglect their deflection in the analysis of the slabs, then we can adopt the method based on coefficients which is given in Annex D of IS 456-2000. In this lecture, we shall cover the method for flat slabs and flat plates and for two-way slabs with deflecting beams, which is given in section 31 of IS 456-2000. For prestressed two-way slabs, the equivalent frame method is recommended by SEI 318-02. It is given in section 31.5 of IS 456-2000. This method is briefly covered in this module for flat plates and flat slabs. The direct design method of analyzing a two-way slab is not recommended for prestressed slabs. In section 31 of IS 456, there are two methods given. One is the direct design method, which is the simpler method and is applicable for reinforced two-way slabs if certain conditions are satisfied. But for prestressed two-way slabs, the second method, which is called the equivalent frame method, is recommended. This recommendation comes from the building code requirement published by the American Concrete Institute and which is denoted as SEI 318-02. The slab system is represented by a series of two-dimensional equivalent frames for each spanning direction. An equivalent frame along a column line is a slice of the building bound by the center lines of the base adjacent to the column line. As the name suggests, that the equivalent frame method is based on defining equivalent frame in each orthogonal direction. Depending upon the number of types of frame in each direction, the building is analyzed for each frame, and then the reinforcement is decided based on the analysis of each frame. The width of the equivalent frame is divided into a column strip and two middle strips. The column strip, which we shall denote as CS, is the central half of the equivalent frame. Each middle strip, which we shall denote as MS, consists of the remaining portions of two adjacent equivalent frame. In the following figure, we shall use L1 as the span of the equivalent frame in a bay, L2 as the width of the equivalent frame. This is the tributary weight for calculating the loads. Let us try to understand the concept of equivalent frame by this sketch. As I had told before, that the equivalent frame is defined in each orthogonal direction. That means in this figure, once we see the plan, we identify a column line. Say in this case we have identified the column line 2, and for the column line 2 we are defining an equivalent frame which is spanning in the direction of the column line. The span in a certain bay is denoted as L1 and the width of the equivalent frame is denoted as L2. The width runs from the center line of one bay to the center line of another bay. The shaded part is the equivalent frame along column line 2. Now the equivalent frame is further divided into a column strip which is the central half of the equivalent frame around the column line, and the two portions which lies outside the column strip are referred to as middle strips. Note that each middle strip consists of two portions from two adjacent frames. That means the middle strip on the left has one part from the equivalent frame along column line 1, and it has another part from the equivalent frame along column line 2. And this is the first way to define an equivalent frame given the building plan. Now once we have defined the equivalent frame in the plan, we see also the equivalent frame in the elevation. The elevation depends on the number of stories, and it also depends on whether there are any breaks in the columns or not. Now given this equivalent frame, we start the analysis. The analysis is done for each typical equivalent frame. An equivalent frame is modeled by slab beam members and equivalent columns. The equivalent frame is analyzed for gravity load and lateral load if required by computer or simplified hand calculations. Next, the negative and positive moments at the critical sections of the slab beam members are distributed along the transverse direction. This provides the design moments per unit width of a slab. That means the procedure is, once we have defined the equivalent frame, we analyze the equivalent frame for the gravity loads, which is the dead load, live load, or if there is snow load at the roof, and we may also analyze it for lateral loads like wind or earthquake. And after the analysis is done, we find out the moments in the critical sections. We find out the moments in the span, we find out the moments near the supports, and once we find out the moments, we distribute the moments throughout the width of the equivalent frame, from which we calculate the moment per unit width of the slab. Now while building the equivalent frame, we need to define the slab beam member, which are the horizontal members, and the equivalent columns, which are the vertical members. If the analysis is restricted to gravity loads only, then a simplified method of analysis can be followed. In this sketch, we find that the columns are assumed to be fixed to the remote ends. That means for a particular floor level, we can analyze that by itself, and what we assume is that the columns at the far ends from that floor are fixed. That means we are not considering any influence from the loads of other floors on the moments of this floor. And once we analyze a typical floor like this gives the results for most of our floors, because usually the loading is similar for many floors, and hence our calculation gets much simpler as compared to analyzing the complete frame. The steps of analysis of a two-way slabs are as follows. First, under the loads, determine the factored negative and positive moment demands at the critical sections in a slab beam member from the analysis of an equivalent frame. The negative moment will be denoted as mu minus and the positive moment will be denoted as mu plus. Thus, once we have analyzed the equivalent frame, we get these two moments. Next, distribute mu minus to the column strip and the middle strip. The column strip moment will be denoted as mu minus Cs and the middle strip moment will be denoted as mu minus Ms. Similar to mu minus, we also distribute the positive moment mu plus to the column strip and middle strip, and those are denoted as mu plus Cs and mu plus Ms respectively. Third, if there is a beam in the column line in the spanning direction, distribute each of mu minus Cs and mu plus Cs between the beam and the rest of the column strip. This is a special case if we have beams along the spanning direction for two-way slabs with deflecting beams. In that case, the column strip moment is divided into the portion that goes to the beam in the spanning direction and the portion which goes to the rest of the column strip. The fourth step is add the moments mu minus Ms and mu plus Ms for the two portions of the middle strip which are from adjacent equivalent frames. We have calculated the middle strip moments for one equivalent frame. We can calculate the middle strip moment from the adjacent equivalent frame, and since a middle strip consists of two portions from two equivalent frames, we add these two moments and get the total moment over the middle strip. Fifth, calculate the design moments per unit width of the column strip and middle strip. Thus, once we get the total moments acting in a column strip and a middle strip, and given their width, we can find out what is the moment per unit width of the column strip and middle strip, and based on the moment per unit width, we can design the reinforcement. Once the design moments per unit width of the column strip and middle strip are known, the steps of design for prestressing steel is same as that for one-way slab. The profile of the tendons is selected similar to that for continuous beams. We had studied how to design the prestressing steel for a one-way slab. Now, for a two-way slab, once we know the design moments per unit width, then the design is similar to that of one-way slab, and the selection of the cable profile is similar to continuous beams that we had studied earlier. The flexural capacity of prestressed slab is controlled by total amount of prestressing steel and prestress rather than by tendon distribution. Still, some guidelines is given on the tendons distribution. It has been found that the flexural capacity of a slab is governed by the total amount of the prestressing tendons and the prestressing force. That means it is independent of the distribution of the prestressing tendons. Hence, there is flexibility in placing the prestressing tendons, but still there are some guidelines to distribute the tendon. The maximum spacing of tendons or groups of tendons should be limited to 8 times h or 1.5 meters, whichever is less. Here h is the thickness of the slab. Thus, the maximum spacing of tendons or groups of tendons should be 8 times the thickness of the slab or 1.5 meters, whichever is less. A minimum of 2 tendons shall be provided in each direction through the critical section for punching shear around a column. The critical section shall be described in the next module. We had seen that around the column, that area is subjected to higher reinforcement, and it is recommended that at least two groups of tendons should pass through the critical section around the slab to column junction. Now, the definition of critical section will be covered in the next continuing module. Grouping of tendons is permitted in band beams. That is, the purpose of having a wide beam is to accommodate the tendons in its width. A minimum amount of non-prestressed reinforcement is provided in each direction based on temperature and shrinkage requirement. As per IS 456-2000, clause 26.5.2.1, the minimum amount of reinforcement, which is AST mean in millimeter square, for unit width of slab is given as follows. AST mean is equal to 0.15% times 1000 times H for Fe 250 grade of steel, and AST minimum is equal to 0.12% times 1000 times H for Fe 415 grade of steel. Here we are considering a unit width of the slab in each direction, and hence the breadth is equal to 1000 millimeters, and the reinforcement is based on the total cross section of the unit width of the slab. Next, we are describing some features in modeling and analysis of an equivalent frame. First, the cross section versus cracked section. So, the difficulty in analyzing a reinforced concrete structure is that the sections may become cracked if the load exceeds the service loads. The chances of cracking are of course reduced when the slabs are pre-stressed. The code allows us to use the gross cross section instead of the cracked section, which is difficult to find out. Thus, for determining the stiffness of the members, cross section can be considered in place of cracked section. When we are developing a model in a computer, we have to assign the stiffness of the slab beam members and the column members. We can assign the cross sectional properties, and if we are consistent throughout the building, then the forces does not make any difference if you have assigned cracked section properties. Since the gross cross section properties are easier to calculate, the code allows us to use the cross section properties. Second is the concept of equivalent column. The actual column needs to be replaced by an equivalent column to consider the flexibility of the transverse beam in the rotation of the slab. The portions of the slab in the middle strip rotates more than the portions in the column strip because of the torsional deformation of the transverse beam. Let us understand this by a sketch. This is a sketch of a slab to column junction, and we have split to show the behavior across the width of the equivalent frame. The arrows represent the rotation in the slab. If we are closer to the columns, then the rotation is less. As we are moving out from the columns, the rotation increase. Thus, the flexibility in the slab is more away from the columns than closer to the columns. To account for this increased flexibility as we move out from the columns, an equivalent column is defined in place of the actual column. The transverse beam need not be a visible beam, but a part of the slab in the transverse direction, bounded by the edges of column or column capital. In presence of beam or drop panel or column capital, the cross section of the modeled transverse beam is taken as follows. In this sketch, we are seeing that what is the cross section of the transverse beam that is considered. As I said, that the transverse beam need not be a visible beam. It can be a part of the slab which is bound by the column. In this figure, in the right hand side, there is no visible beam, but the modeled transverse beam is the part of the slab which is bound between the column faces. In the middle one, there is a column capital and a drop panel, and we see that the part of the drop panel which is bound within the column capital is selected as the transverse beam. And in the first figure, there is a visible transverse beam, and if there is a transverse beam, then we also consider a part of the slab to be a part of the transverse beam, and this part of the slab is determined by a 45-degree projection of this outstanding part of the transverse beam. Thus, once we are able to identify the transverse beam, we can find out the properties of the equivalent column. The flexibility of the equivalent column is equal to the sum of the flexibilities of the actual column and the transverse beam. This is the basic idea of defining the equivalent column, that we are adding up the flexibilities of the column and the transverse beam in the rotation of the slab to column junction. 1 by KEC is equal to 1 by sigma KC plus 1 by KT. Here we are adding the flexibilities to consider the increased rotation of the slab as we move away from the column. KEC is equal to the flexural stiffness of the equivalent column. Sigma Kc is equal to Kc upper plus Kc lower, where Kc upper is the flexural stiffness of the upper column, Kc lower is the flexural stiffness of the lower column, and Kt is the torsional stiffness of the transverse beam. Thus, what we see in this expression is the adding up of flexibilities which are inverse of stiffness. Kc is the flexural stiffness of a column, and Kt is the torsional stiffness of the transverse beam. And when we appropriately add the flexibilities, we get the flexibility of the equivalent column, from which we calculate the stiffness of the equivalent column. An approximate expression for the flexural stiffness of a column Kc is given as follows. Kc is equal to 4 EC times IC divided by L minus 2H. This is very close to the expression that we learned from the slope deflection methods in basic structural analysis. EC is the modulus of concrete, L is the length of the column, H is the thickness of the slab, and IC is the moment of inertia of the column. Thus, we have an expression of the flexural stiffness of a column, which we can apply to the upper column and the lower column. An approximate expression for the torsional stiffness of the transverse beam Kt is given below. Kt is equal to 9 times EC times C divided by I2 times within bracket 1 minus C2 divided by L2. Here C is the equivalent polar moment of inertia of transverse beam, C2 is the dimension of the column in the transverse direction, L2 is the width of equivalent frame. For a rectangular section, the expression of C is given below. Note that C is a quantity which is analogous to the polar moment of inertia for a circular section. For a rectangular section, such a quantity is difficult to define exactly, an approximate expression is given as follows: C is equal to the summation of within bracket 1 minus 0.63 times x divided by y times x cube times y divided by 3. The summation is taken over the component rectangles of a compound section, which we shall come later, but let us first understand what is x and y. Here x and y are the smaller and larger dimensions of the transverse beam for a particular rectangle. The expression of C is a lower bound estimate, that is, the calculated value is always lower than the actual moment of inertia of the transverse beam. Again, as I have said, that this is an approximate expression of a quantity which is equivalent to the polar moment of inertia for a circular section. Now, when we have a compound section, we make a summation over the individual rectangles to find out the value of C. The splitting of the compound section into component rectangles should be such so as to maximize the value of C. As I said that C is anyhow a lower bound, that means the actual value cannot be lower than the value calculated based on the individual rectangles, and hence we can divide a compound section in such a way that we can get the maximum value of C, which anyhow will be lower than the true value. For the following two cases of splitting, select the larger value of C. Thus, if we have an L-shaped transverse beam, then we can either split it into two rectangles as shown on the left, or we can split into two rectangles which is on the right. Now, for each rectangle we have to identify x and y, which are the smaller and larger dimension respectively, place those values in the expression, take the summation, calculate the value of C. Now, once we have got the values of the C for both these schemes of splitting, we pick up the value which is higher. Thus, once we calculate C, and from the other geometric properties we can find out the transverse beam stiffness, the torsional stiffness, which is denoted as Kt. If there is a beam in the column strip in the spanning direction, then Kt is replaced by Kt times ISB divided by Is. Here Is is moment of inertia of slab without the projecting portion of the beam, as shown in the shaded area in figure A. That means in this figure, whatever has been shaded in the cross section of the slab beam member without the projecting beam is considered to calculate Is, and ISB is the moment of inertia of slab considering it as a T section, shaded area in figure B, and ISB considers the full cross section of the slab beam member. Thus, if there are beams in between the column lines which may be present in a two-way slab with deflecting beams, in that case we reduce Kt to consider the flexibility of the beam also, and it is reduced, it is changed proportionately. Third, we are defining the slab beam members. The variation of the flexural moment of inertia of a slab beam member is considered as follows. The value of the moment of inertia is constant, say equal to I1 in the prismatic portion, that is in between the faces of the columns or column capitals or drop panels. It is also constant with a different value in the region of a drop panel. The slab beam member is the horizontal member. Its flexural stiffness is different in the span as compared to the values in the drop panel. What values to be picked up is recommended by the code, that since the moment of inertia varies in the region from the face of the column or column capital to the center line of the column, it is approximated to a constant value equal to the following: I2 divided by 1 minus C2 divided by L2 whole square. Here I2 is the value at the face of the column or column capital. Let us understand the recommendation by the help of a sketch. The top figure is the elevation of an equivalent frame at a particular floor level within a bay, and we see that the flexural moment of inertia is varying along the span of the slab beam member. In the middle region, it is constant to a value of I1. Near the drop panels, it has a value of I2, and from the face of the column capital to the center line of the column, it varies. The code says that in this region, from the face of the column capital to the center of the column, we can consider a flexural moment of inertia equal to I2 divided by 1 minus C2 by L2 whole square. Thus, for this particular case, we have three values of the moment of inertia for the slab beam member: I1, I2, and finally a value which is from the face of the column capital to the center line of the column. The fourth point is the arrangement of live load. Since the factored live load WULL may not occur uniformly in all the spans in a floor, a distribution is considered to generate the maximum values of the negative and positive moments at the critical sections. When we are applying the gravity load, we have to be careful that if the live load should be placed uniformly or not. The dead load can be placed as is given for the member sections, but the live load may not be uniform throughout the span and for the different spans in the equivalent frame. The codal recommendation is that if the distribution of WULL is known, then the load is applied accordingly. If the distribution is not known, then a pattern loading is considered based on the value of WLL with respect to that of the factored dead load WUDL. Of course, the load case with WULL on all the spans should also be analyzed. Let us understand this by the help of a sketch. For the live load to be less than 3/4 of the dead load, which is the case for most of the buildings, the possible variation in WULL in the different spans is neglected. Thus, the live load can be applied uniformly only if the live load is less than 3/4 of the dead load. And in this sketch, you see that the live load has been applied uniformly in all the spans, and we are analyzing the member with that loading scheme. If the live load exceeds 3/4 of the dead load, that means the live load is substantially high, then for maximum moment of mu plus in a span, 3/4 of WLL is applied on the span and alternate spans. For example, if the maximum value of mu plus in span BC of the frame below is to be determined, then 3/4 of WULL is placed in spans BC and DE. That means, if we are looking for the mid-span moment of BC, we shall place the live load in BC and alternate span like DE, and the value of the live load is 3/4 of the live load coming in the tributary width, which is WULL times L2. For maximum value of mu minus near the support, 3/4 WLL is applied on the adjacent spans only. For example, if the maximum value of mu minus near support B is to be determined, then 3/4 WLL is placed in spans AB and BC. Thus, if you are looking for the negative moment at the support, then we place the live load only on the adjacent spans. Thus, we have placed the live load in AB and BC only. This may give a critical value of the negative moment at B. Of course, we also have to analyze the case where the live load is uniformly placed in all the spans. That means from these load conditions, we find out the maximum values of the positive moments in the span and the negative moments in the support, and these maximum values are called the envelope values from which we design our slabs. The fifth consideration is the defining the critical section near a support. The critical section is determined as follows, that at an interior support, it is the face of support, which is the column or column capital if any, but not further than 0.175 L1 from the center line of the column. For an exterior support, it is at a distance from the face of column not greater than half the projection of the column capital if any. Next, we are understanding the distribution of moments to the two strips, column strips and middle strip. In absence of a rigorous analysis, say finite element analysis, the procedure for reinforced concrete slabs may be used to distribute the moments mu plus and mu minus to the column strip and middle strip. Of course, SCI 318-02 does not recommend the procedure to be used for prestressed slabs. Thus, we can use this procedure of distributing the moments with caution. It is preferred that we do a more rigorous analysis to find out the moments in the column strip and the middle strip. The first is that the distribution of mu minus and interior support is as follows, that for the column strip it is 75% of mu minus, for the middle strip on the two sides the total moment is 25% of the mu minus. Remember that mu minus ms is the total negative moment in the two middle strips in the two sides. For distribution of mu minus at exterior support, if the width of the column or wall support is less than 3/4 of L2, then mu minus Cs is the total moment at the support, which is mu minus, and the moment in the middle strip is 0. If the width of the column or wall support is greater than 3/4 L2, then mu minus is uniformly distributed along the width L2. Thus, depending on the width of the column with respect to the width of the equivalent frame, we decide upon whether the full negative moment should come to the exterior column or not. Third, the distribution of mu plus at midspan. The column strip gets 60% of the positive moment and the middle strip gets 40% of the positive moment. Again, note that for the middle strip, the mu plus ms represents the total positive moment in the two middle strips at the two sides. The total moments in middle strip, which is mu minus ms and mu plus ms, are distributed to the parts of the two middle strips at the two sides of the equivalent frame proportional to their widths. The combined middle strip from two adjacent equivalent frames is designed for the sum of the moments assigned to its part. That means for one particular equivalent frame, the value that we have got for the middle strip, we distribute that in the two portions of the middle strip at the two sides. Now, once we have distributed, for each middle strip, we combine the two values from one equivalent frame and the adjacent equivalent frame to get the total moment in that particular middle strip. Thus, in today's lecture, we have introduced the two-way slabs. We said that for a non-rectangular slabs are always designed as a two-way slab, and a rectangular slab, if it is supported on all the four sides, then it is designed as a two-way slab depending on the length to breadth ratio. If the length to breadth ratio is less than 2, then we design the rectangular slab as a two-way slab which spans in both the directions. Now, there can be different types of two-way slabs. The first is a flat plate which does not have any beams or drop panels or column capitals. The second type is the flat slabs which does not have any beam, but it can have a drop panel or column capital. And the third type is a two-way slab with beams, where beams are running in between the column lines. Now, the flat plates can have beams at the edges which are called spandrel beams. The design of two-way slabs can be done by two methods. For flat slabs and flat plates, the method is given in section 31 of IS 456-2000. This method is also applicable for two-way slabs with beams that can deflect, and there is a second method which is for the two-way slabs whose beams are stiff enough and their deflection can be neglected. That method is given in the Annex D of IS 456. In this module, we discussed the section 31 of IS 456, which is the one which is used conventionally for flat plates and flat slabs. Now, again in that section, there are two methods given. One is the simplified method, which is called the direct design method. Now, this is not suitable for prestressed slabs. The second method, which is the equivalent frame method, and it is based on a computer analysis, that is recommended for two-way prestressed slabs. In the equivalent frame method, first we define the equivalent frames in each orthogonal direction. An equivalent frame is a slice of a building along a column line whose width spans between the center lines of the two adjacent bays. Now, within an equivalent frame, we define a column strip and two middle strips at the sides. Now, once the equivalent frame is defined, we analyze that frame for gravity loads and lateral loads, if any, and find out the moments in the critical sections, the positive moments in the span and the negative moments in the supports. Now, once these critical moments are known, then we distribute that moments along the width of the equivalent frame, from which we calculate the moment per unit width of the slab. Once we know this value, we can design the pre-stressing tendon just the way as we had done for one-way slab. In our next lecture, we shall move on to the design for shear of two-way slabs. Thank you.